So my name is Hyungnae Kim, Vice Dean of Research, and it's a privilege to welcome you to today's lecture in Professor Badoo Jena Endowed Distinguished Lecture Series. First, I'd like to express our sincere appreciation for the opportunity this outstanding lecture series provides to our faculty, students, and trainees. It's not often that we have the chance to come together to learn directly from leaders at the very highest level of science. And today is especially special as we honored to host the Nobel laureate, Dr. Roberts. This is exactly the kind of inspiring and intellectually enriching experience that elevates our academic community. Before we begin today's lecture, it is my great pleasure and honor to acknowledge Professor Badoo Jena, who established the Jena Distinguished Lecture Series. Dr. Jena is George E. Palate University Professor and Distinguished Professor in the Physiology Department at Wayne State School of Medicine. He is an internationally recognized leader and renowned scientist in cell biology and nanoscience. Professor Jena received a PhD in molecular endocrinology from Iowa State University, and he was the founding director of Drug and Discovery Center at Yale University. And here at Wayne, he founded Institute of Nanobioscience and promoted interdisciplinary research. One of his most groundbreaking contributions is the discovery of porosome, which is the universal secretory machinery in cells. This work represents paradigm shift in biology, demonstrating that secretion is a highly regulated sequential process rather than an on and off or all or none process. His pioneering application in application of atomic force microscopy to living cells enabled nanoscale visualization of cellular structures and opened entirely new avenue for cell biological discovery. Professor Jena has been recognized worldwide. He's a fellow of American Association for the Advancement of Science and has received numerous prestigious honors, including George E. Palate Award Gold Medal, the Sir Aaron King Award, and 2024 Camurus Lipid Science Prize. He has also been elected to several international academies and awarded multiple honorary doctorates. Beyond his scientific achievement, Professor Jena has shown exceptional leadership in translating discovery into innovation, and he founded companies focused on advancing novel therapeutics. And Professor Jena, thank you for your vision and leadership in establishing this remarkable lecture series and for bringing distinguished speakers to our community. Next, I'll have Dr. Wertz introduce today's speaker, Professor Roberts. Thank you.
What can you say when you're trying to introduce a Nobel laureate? What hasn't already been said? I'm going to take leave of absence from any obligation here and allow Sir Richard to introduce himself, because he's going to tell us the story of his career from beginning to end. And there's no way I could borrow phrases from any publicly available source that would do justice and not contradict what he's about to present to us. So Richard, without further ado, let me introduce you and bring you up for your talk.
Very well, thank you. It's a great pleasure to be here. I'm always honored when I I'm invited to give talks of this sort. And I especially like talking about my career in science because I think there are a number of really interesting aspects of my career that will play well with students. And I will try to point out some of these. One of the things that you will see throughout the talk is the importance of luck. I am probably the luckiest person you know. You may think you know lucky people. Wait until you hear what I have to tell you. So I was born in Derby, shown here, A, and this was in 1943, while the Second World War was still going on. And Derby was an interesting place to be because it was right next to the Rolls-Royce factory that was making all of the engines for the fighters that were going over to Germany. And Germans were very keen on bombing it. And they flew over the street on which I was living. Well, actually, I was born there. And on their way to the Rolls-Royce factory. And they were not very accurate about their bombing. And quite a lot of the bombs, instead of going to the Rolls-Royce factory, ended up on our street. And one side of the street was almost completely destroyed, but I was lucky, it was not my side. I could easily not be here, but for the bad aim of some of these German bombers. Now, when I was 4 years old, my father, who was a motor mechanic, he left school when he was 14 and gone off and worked in the local council doing mechanics and various things. Got offered a job in Bath on the bottom left of the slide. And it turned out we had to move down there, and I moved down there. And that was probably one of the very good things that happened to me, because Bath is a beautiful city. I don't know if you've been to England. If you have you visited Bath? If not, then the next time you go and visit. It's one of the very beautiful cities in England. So anyway, so from age 4, that's where I was. Now, when I was first got there, I went to a local school. But then by age 7, I went to St. Stephen's School, shown here. And that also turned out to be a very interesting aspect of my life, because one of the things I discovered, well, it was a very small school. There were 4 forms and sort of 25, 30 kids in each class. And one of the things that used to happen to me, after I guess by the time I was about eight or so, was the headmaster used to come up and give me puzzles at the end of the day to take home. And those puzzles were mathematical puzzles. And I fell in love with mathematics. If you'd asked me until I was about age 10 or so what I was going to do with my life, I would have told you I was going to be a mathematician. I absolutely loved it. And it was because the mathematical problems were really puzzles. And I've always enjoyed puzzles and solving puzzles. So that was very good. And I also, during that time, read a book that I forget where it came from, but it was entitled How I Became a Detective. And it was about how one traditionally became a detective in the police force in England. And by the time I finished that book, I knew I wanted to be a detective. So this was something else that I wanted to do. I thought it was great. And then my father made an interesting thing. And he bought me a chemistry set when I was 11 for Christmas present. And I've got to say, I should say that my parents were not well off. We had very little money. And my mother stayed home. She looked after me. My father had this job as a motor mechanic. And so it was quite a lot of money for them to buy me a chemistry set. But I can tell you, this was in the days when chemistry sets were real chemistry sets. None of these watered down things that you buy today. And I discovered fairly soon that I could make fireworks and I could make explosives with the chemicals in this set. And I was overjoyed. I managed not to lose any fingers or anything, but I loved it. And so by the age of 11, I knew I was going to be a chemist. So here we are. Over a short period of time, I went from mathematics to detective to chemist. And when I look at my life now, all of those things I do. I do research. I'm a detective. I do bioinformatics. That's mathematics. And chemistry, well, chemistry is the basis of biology, and I work on biological things. So this period of my life had a huge influence. And one thing that I will say is I kept switching from one thing to another. I found something that's more interesting, I would pursue it. And I've done that throughout my life, and I would recommend that to all students, that when you come across something that is more interesting than what you're doing at the moment, don't be afraid to switch, because the people who are happiest in this world are the people who are pursuing the stuff they love to do. It's their hobby. You don't work, okay? This is what you do for a living. I don't think I've worked a day in my life because I've always pursued things that I love to do. Now, one of the things that happens when this is Bath, England, one of the reasons why you should go and visit, on the bottom left are the Roman baths. This city was set up by the Romans because there were hot springs there. On the right, some of the architecture there, it was built in the Georgian period, a beautiful architecture. And it's all in local Bath stone, which is really very nice. Now, at age 11, one of the things you had to do was to go to a secondary school of some sort. And there were two basic schools you could go to. One was a grammar school, if they thought you were going to be interested in some things more academic and maybe go to university or something eventually. Or if they thought that perhaps you were better off suited for a technical operation, then you would go to a technical school. So, and the way they decide is they give you something called the 11+ examination, which is an examination to find out which of these paths you should pursue. And I can tell you that is the best example of an exam that I've ever experienced. We all showed up at school one day. We were sat down at our desks, given some papers and asked to fill in these papers, which we did, and then hand them in at the end of the lesson. And it turned out this was the 11+ examination. We had no idea, no way to prepare for it. Either you knew the stuff or you didn't. And the questions were very straightforward. And I've always thought that is the best way to conduct examinations. This idea of swatting before an exam, oh, I hate it. Awful. Either you know the stuff or you don't. If you know the stuff, then you can take the exam. If you don't know it, then you fail. Anyway, this was the City of Bath Boys School where I went to. I increased my love of mathematics. We had a wonderful math teacher there, so that was good. I learned to play the violin, joined the school orchestra. I also became very interested in caving. So the area just south of Bath is the limestone hills of the Mendips. And they have some wonderful caves there. And I got really interested in caving. I would say I became very proficient at this. And I also discovered jazz, which I like very much. So Bath, it turns out, is very famous for jazz. Now, during my time in that school, I also found something rather interesting. So I almost got thrown out when I was 18, because what had happened is after you take the ordinary level exams, which determine whether you're going to go on a more academic thing or they're going to throw you out and you've got to do something else. The first year was all interesting stuff, ready for the advanced level examinations. The following year, they just repeated everything. And it was the most boring year of my entire life. And so I stopped going. I used to go in the morning, sign in, then leave, and I'd go and play billiards or snooker at the local YMCA. And then about 4 o'clock, I'd go back up to school, sign out to indicate I'd been there all day. And unfortunately, there was a physics teacher who decided that was not good. And he tried to get me thrown out of school. But what I discovered by playing billiards and snooker was the importance of luck. So I was the West of England junior snooker champion. I was really good at this game, I got to tell you. In fact, I thought about becoming a professional snooker player, I've got to say. But I learned an incredibly important lesson. And that was I was playing in a tournament and I was trying to pot one of the red balls. And the one I was trying to pot, I missed, but I got another one in by mistake. And then the next shot, instead of really concentrating, I messed it up. And this old gentleman, you know, I was 18 at the time, this old gentleman came up, he must have been in his 80s. He said, you could be a great snooker player, he said, but you have to learn the importance of luck. When something lucky happens, you've got to take advantage of it. And that means you've got to concentrate twice as hard on the next thing you do. And I think that is some of the best advice I ever got in my entire life. And I would recommend you all do the same. It's interesting to look back and see how luck played some role in your life and then ask, well, there was a lucky break. Did I really take full advantage of it? Well, I hope the answer is yes. Anyway, I went to audition to become a professional snooker player when I thought I was going to be thrown out of school. But unfortunately, the headmaster decided he wasn't going to throw me out, and so he took me back. I always feel I've missed my chance to be really famous. I could have been world champion. I tell you, I was that good. I'm sure I could. So when it came time to go to university, I'd actually missed 1 year of school because of this incident of not bothering to go. And I failed physics the first time when we took the advanced level examinations. So I had to stay for an extra year. And at that point, I couldn't go to Oxford or Cambridge. They don't let you go. And so there were two universities that I applied to do chemistry. One was Southampton and one was Sheffield. Southampton turned me down. So by chance, I ended up at Sheffield. And that turned out to be really, really a good place. I could not have wished for a better place to go and first be an undergraduate and then to be a postgraduate. So I got my BSc in 1965, and I stayed on to work with this gentleman, Professor Ollis, who was professor of organic chemistry. And he was really good. When it came to taking exams from him, you couldn't swap for them. You never knew what was coming. You would be said, oh, here's a compound that I found. I did this, and to it, and this is what happened. What is it? And this was the kind of questions that he asked. You couldn't swap for this. It was impossible. And so I was really happy when he agreed to take me as a graduate student. And Sheffield is a very interesting place. It's in the sort of center of England, a little north of Derby. It was an old steel town, and that was pretty good. But when I was there and doing my PhD, I met a guy called Kazu Kurosawa, and he was my real mentor in Sheffield. He was a postdoc from Japan. He taught me everything about how to do experiments. He would look at a problem and he would say, oh, I think this is a good thing to do. You should do this and this and this. And then he'd tell me exactly how to do it. And then when we got the results, he would tell me exactly how to interpret the results. And he was with me for a year, or I was with him for a year. He also taught me how to play Go, which is a wonderful game. If you've never come across it or tried it, do try it. It's a great game. And we actually, after he left and went back to Japan, I played Go with him by mail. You know, in those days, there was no email. We played by mail for a couple of years until his English got so bad, it became clear he was having trouble writing the letters to go along with the move. But in my third year, well, I should also say after my first year, I pretty much had everything I needed for my thesis. I could have written my thesis then, but this was all thanks to Kazu. But you have to spend 3 years. And so the second year I was doing stuff on my own, and some of it worked and some of it didn't. But the third year I spent a lot of time in the library. And I came across this book by John Kendrew called The Thread of Life. And this is a very interesting account of the origins of molecular biology. And it was one of these things that, you know, I read it. I must have read it twice. By the time I'd finished, I knew this was what I wanted to do with my life. I wanted to be a molecular biologist. Forget all this other stuff. I wanted to be a molecular biologist. And so I went and told Professor Ollis that this was what I wanted to do. And he said, oh, there's no such subject. Remember, this is some time ago. And all of the other people in the chemistry department, all the assistant professors, they all said, there's no such subject. Why do you want to do that? Except for one. There was one called Mike Blackburn, who was a young associate professor. And he said, do it. This is good stuff. This is something that's going to be interesting. And he gave me some ideas of where to apply to do a postdoc in order to pursue molecular biology. Now, you have to understand in England in those days, if you went and did a postdoc in England, the chances of getting a job in England in a university were zero. You had to go abroad and get away from England if you hoped to get a job to go back. So I applied abroad. I actually applied to 6 different labs, people who had been chemists and had moved into biology or biochemistry or into this area. And I applied to 6 of them, and only one accepted me. And the one who accepted me was this gentleman, Jack Strominger. And incidentally, he's still alive. He turned 100 last year and is doing pretty well. And he took me on, and I thought I was going to Wisconsin, because when I applied, he was at Wisconsin. A month before I was scheduled to go over and join him, he said, "Oh, can you delay for a month, because I've just been appointed a full professor at Harvard," which turned out to be his lifelong dream that he wanted to do. And so I ended up at Harvard instead, purely by luck. I had no idea that this was where I was going to go. But it turned out that Harvard was a pretty good place to go, and Jack took me. But one of the best things that happened was that he just achieved his lifelong ambition, and he took the opportunity to change fields. And so I was given a project together with a postdoc who'd been with him for 2 or 3 years to finish up this sequencing of a transfer RNA. And Jack wasn't really interested. He just wanted the project finished. And so he let me do whatever I want. And one of the things I did, as soon as in those days, people were sequencing tRNAs by a lot of old-fashioned methods that had been developed by Holly. But I started to read about this and discovered there was this gentleman, Fred Sanger, who was at the MRC lab in Cambridge, who had developed a method of sequencing RNA that involved labeling the RNA with P32 and then doing a variety of things that you do to take advantage of the labeled material. So I asked Jack and said, can I go over to Fred's lab and learn how to do this? He said, sure. Wrote to Fred. He said, oh, please come. So I went and spent 6 weeks at the MRC lab in Cambridge learning how to sequence tRNAs. And it was wonderful. I don't know if any of you are familiar with the MRC lab in Cambridge. It's a very good place. I think they have 7 Nobel laureates who went through there. I don't include myself. I just went there as a visitor. But they had a wonderful place. And they had a method of doing research, which meant that anyone who was an investigator there maybe could have a lab of 2 or 3 people, but no more. And so if you wanted to do a big project, you had to collaborate with someone else at the lab. And that's a very good way of doing science. I really recommend that heartily. You don't want to do it all yourself. If you talk and find a collaborator, you can learn a lot from that collaborator. Anyway, so I came back to Harvard, and Jack, because he'd just been appointed as this big professor, had money, unlimited money, and he set up a chromatography lab where I could do everything that I'd been doing in Fred Sanger's lab. It was sort of a mini Fred Sanger's lab. He set it up at Harvard for me. And so I started doing that. And that turned out to be very good because I was the first person in the Boston area to be using Fred Sanger's techniques at the time. And so everybody came to me to learn how to do it. Wally Gilbert came to me to learn how to do it. Mark Potashny came, Tom Manias. They all came to learn. And I made so many good friends in those days. And it is worth noting that this idea of networking and making contacts and getting to know other scientists is incredible. I mean, this is the way that you make progress, because you're doing a project and you hit a problem, you think, don't quite know how to do that, but oh, I remember so-and-so, maybe he can help me. And if you've made good friends and good networking, you can go and ask and they will help you. I have people today who learned how to sequence from me at Harvard who have come to me and will say, I'll do something for them or they'll do something for me. And so this networking is really important. And I always like to make one other comment, that the nice thing about science is that wherever you go, if you meet a scientist, you have a friend. Scientists are great people. And if they disagree with you, you can disagree violently about stuff, but we don't find it necessary to shoot one another to show who was correct. I think scientists make some of the very best diplomats, much more so than politicians. So while I was at Harvard, I ran into Jim Watson, I didn't quite run into him. What happened was Mark Potashny came to me in a seminar one day and said that Jim Watson was looking for someone to sequence SV40 DNA at Cold Spring Harbor. And he said, Jim's going to come and talk to you because he thinks you would be a good candidate for this. And so 2 weeks later, no word from Jim. And Mark comes up and he says, well, Jim doesn't actually know who you are. Perhaps you can go and introduce yourself. And it was obvious that Mark had recommended me. Anyway, so I go and I walk into Jim's office, knock on the door, walk in, and he says, oh, I want you to come to Cold Spring Harbor, he said. This was straight out of the blue. And then he told me a little bit about what he wanted. And then he said, as I was there, I say 10 minutes. I think that's an exaggeration. It was probably really only 5. As I was walking out of the office, he said, oh, you should probably come down to Cold Spring Harbor and see what we're all about and see what kind of lab it is. And, you know, and he said, but it's not an interview, he said. You got the job. It's not an interview. So I did go down and ended up going to Cold Spring Harbor Laboratory and had a very good time there, very interesting time there, including meeting a lot of good people and having good postdocs. And it was good. It was a very good time. But what Jim wanted me to do was to sequence SV40 RNA using existing techniques. And I found there were 2 other labs doing the way I would have done it, or the way he wanted me to do it, which was to copy the DNA into RNA, sequence the RNA, and then put the bits together. Now, there were 2 other groups already doing that, one at Yale and one at Ghent in Belgium. And I hate doing things that other people are doing. I don't like it. I want to do things I thought about, not things that somebody else thought about. Now, just before I went down to Cold Spring Harbor, I'd gone to a lecture by Dan Nathans. Dan is the person in the top left of this picture. He was a Nobel laureate. He gained the prize together with Werner Aber in the middle and Ham Smith at the bottom for the discovery of restriction enzymes and figuring out how they could be applied. And really, these discoveries set the scale for the whole recombinant DNA industry. This got everything started. And when I went there, I thought, well, you know, there were, I think, 3, 4 enzymes were known. They all recognized different sequences. And I thought, well, if there are more of these, maybe we can use these to sequence DNA. Forget about all this stuff with RNA and copying and so on. And I thought, you know, I can develop a method, sequencing DNA, something that would be very useful, would be better, and I could do a better job than Fred Sanger. So that's what we started doing. We started looking for restriction enzymes, and it was amazing. Everywhere we looked, we found them. It was unbelievable. Of the first 100 restriction enzymes discovered, 75 were discovered in my lab at Cold Spring Harbor. And it was good because a postdoc could come in, find an enzyme, get a publication out of it, and then do something really interesting. So you don't have to keep doing it, you know. But the grant that we got was to find new enzymes. And it was good. It was really very good. So that's what I decided to do. And Jim Watson wasn't happy about this. So Jim Watson said, I hired you to sequence SV40 using copying it into RNA, doing it the way other people are doing it. I said, well, I thought this was a better way to do it. And he said, no, it's not. I'm going to have to fire you, he said. And he said this, I was in the kitchen. I think there were 3 dishwashers in the kitchen doing their work. And he's yelling at me about how he's going to fire me. This was Jim. Now, I was lucky. So I say, I'm the luckiest guy you know. I had run into this fellow, Norton Zinder. Norton was a professor at Rockefeller University, and he became a very good friend, and he loved restriction enzymes. I met him by accident on a train going to a meeting in Belgium. And he was a very good friend of Jim Watson. And if you were to ask me, I'd say he's one of the few people who was really ever a good friend of Jim Watson. There are plenty of people who knew him, but Norton was a friend. And so he used to call Jim, and especially this first time he called him and he said, "You can't fire Rich. This is really important stuff. Leave him be." And so then Jim would back off and wouldn't fire me. We must have gone through this 10, 15, maybe 20 times while I was at Cold Spring Harbor. Jim constantly wanted to fight because I was doing stuff that he wasn't interested in or he thought was not the way to go. And he's a little like Trump in some ways. So one of the things we started doing as we started getting restriction enzymes, we wanted to determine what their recognition sequences were. And so this was how I got interested in bioinformatics, because I had a postdoc, Tom Gingiris, and he had this idea that there were some things we could do by looking at where restriction enzymes were cutting DNA, looking at the distance between the sites, and then looking at the sequence and seeing, could we find a sequence that matched that? And we wrote a bunch of programs related to that. Some of these are now at BioLabs. We have a set at BioLabs for people who are interested in this sort of thing. And these are all available on the web at BioLabs. But this was what really got me interested in computation. Now, the other thing that happened was I had a postdoc called Richard Gelinas, who had come to work with me from Harvard. He'd been a graduate student at Harvard, and he came down to work with me. And we had this thing that someone would find a restriction enzyme, then you'd find another project to do that was more interesting. And the project he picked was one that we talked about and was working on adenovirus 2. This is a small virus. It's a very nice virus to work with in the lab. It's one of these that almost everybody has had an infection with adenovirus when they were very young. You get antibodies and never have a problem again. So it's nice to work in the lab with this. And we were interested in, was a eukaryotic promoter, did it look like a bacterial promoter? And two promoters had recently been found and sequenced in bacteria, one by Wally Gilbert and one by Mark Potashny. They were pretty similar. So the question was, are adenovirus promoters the same? We knew that in adenovirus, thanks to other work that had gone on at Cold Spring Harbor, that early after infection, transcription came in from the ends of this linear virus. And so we thought, well, if we can find the 5' end of the messenger RNA and then look at the DNA sequence coming in from the end, we can find the sequence just upstream of the start of the messenger RNA, and that would be the promoter. So we got started doing this, and this was Richard Gelinas' project, but it turned out we couldn't get enough early RNA to do this project successfully. We just couldn't get enough. And so we turned our attention to late RNA, because after adenovirus is infected, after a few hours, all of the RNA being made is adenovirus RNA. It's all the late RNA shown here as L1, L2, and so on. And turns out there are quite a lot of different transcripts, maybe a dozen, 15 different transcripts up there. And we thought, well, if we can find the 5' ends of these, then we have another way of going to find a promoter. And so I came up with this, what I thought at the time was a very clever method of finding the 5' ends of the message. Now, in bacteria, the 5' ends of the message were triphosphates, and we assumed that they would be the same in higher organisms, in eukaryotes. But fortunately, before we got too far in the project, the cap structure of messenger RNAs was discovered. And so once that was discovered, I came up with a clever method by which we could isolate just the capped oligonucleotides. I don't want to go too far into the details, but so we started doing this. And when we did this and looked on a 2-dimensional gel, you can see early in infection, 2 to 24 hours, there were 2 5' ends that you could see, but a bit later, there was only 1. Turned out these 2 were related because one was a cyclic phosphate of the other, so they were really the same thing. So the question was, how is this possible? You know, there are 12, 15 different RNAs. How come they've all got the same 5' end? Well, that we spent an awful lot of time, and quite a few postdocs got involved in trying to figure out what the hell was going on here. And it was basically just really annoying because I knew the method worked really well. And first, when Richard got this result, I said, well, you know, do it again, and kept getting the same result. And I said, well, you know, let me do it. I'll show you how to do it properly. I got the same result. So at that point, of course, I believed it. But anyway, this went on. And we wrote a paper on this called One Predominant Undeconucleotide, 11 long nucleotide that was there. And the question was, how is it possible that this can be there? And so we started doing a bunch of experiments to find other ways to isolate it, to test it, to see could we find it on individual messenger RNAs. And it came soon clear that the 5' end, this 5' oligonucleotide, was not coded on the genome next to the main body of the message. It was being coded somewhere else. So the question came, well, where is it being coded? And we thought of this R-loop experiment. So if you have a messenger RNA and you've got the DNA that is coding for it, you can melt the DNA, add the RNA, and you get an R-loop, as shown here at the bottom, because the DNA-RNA hybrid is more stable than the DNA hybrid. And so if there's a sequence at the end of the messenger RNA that isn't coded right next to it on the DNA, then if you do an R-loop, it should be sticking out as a little tail. At the 3' end, you've got poly A, because we know that that is added after transcription. So the thing is, if we could find a good probe that would tell us, that would hybridize to this 5' end of the RNA, then we have an explanation for what's going on. And the experiment was simple. Make an R-loop, find a DNA probe that you think is coding for this. And I became convinced that there was actually a transcription problem or a different way of transcribing RNAs in eukaryotes, and that was to start with a primer, and that this sequence at the 5' end was the residue of the primer. And it turned out in adenovirus, we knew there was a small RNA called VA-RNA. We knew where it was located, and I was beginning to think that that would be the primer. So this was the experiment that we decided to do. We would make the DNA that coded for this VA-RNA, add it to a hybrid, and then look in the electron microscope and see if we got a picture like this. Just one small problem with that. Neither Richard nor I were electron microscopists. So fortunately, just down the hall, there were two very good microscopists, Louise Chow and Tom Broker. And so I'd thought of this experiment on a Saturday. We went down and talked to, they were working on a Saturday, went down, talked to them. And they said, well, you know, this experiment's never been done before, but it should be doable. And, you know, we'll give it a try if you go and make the reagents. So Richard went and made the appropriate reagents, made the R-loops, made the DNA that was going to be used for the hybridization, and then gave the reagents to Tom and Louise, and this is what they found at the bottom. What we were expecting was in the middle. That is, there'd just be a piece of DNA that was hanging on. What they found instead, but this probe DNA was actually hybridizing at two separate positions to the leader on the RNA. And that was the discovery of splicing. Okay, that's all you needed. Every EM picture they looked at all looked this way, no matter what was going on. And already at the end of that day, people were talking about Nobel Prizes because they were sure this was going to be everywhere. And it turned out loads of people already had evidence showing that normal messenger RNA was not being made in adenovirus or in eukaryotes in the way it was in bacteria. And so this became very exciting. Phone calls rushing around all over the place and so on. This was in 1977. So that was really exciting. I remember shortly after we made the discovery, I gave a talk at Cold Spring Harbor and about the discovery. And later in the meeting, I think 3 talks after mine, Mike Bishop gets up, shows his slides, and he says, you know, I have a slide here I'm going to show you that I could not explain until I heard about this. Now I can explain it. And he got really excited, but everybody was so excited about this. It was, you know, just a paradigm shift. This was not the way that anybody thought RNA, messenger RNAs were being made. So we published a paper called An Amazing Sequence Arrangement, 5' ends of adenovirus messenger RNA. And when it came time, we wanted to call it a something sequence arrangement. And I like the word amazing. The other authors didn't. They came up with sort of watered down views about this. But eventually I won over and they accepted it. And we sent it off to the journal Cell for review. Reviewers got back and said, you know, great paper, wonderful work, really a nice discovery, but you've got to change the title. You know, amazing. It's not a scientific word. You can't put it in a scientific paper. And so I got Ben Lewin, who was editor of Cell, said the same thing in the letter to me. He said, you know, we'll take it, 2 or 3 minor revisions, but you got to change the title. So I called him up and talked about some of the other things. And during the conversation, I said, Ben, you know, when you first saw this, what did you think? He said, oh, it was amazing. I said, I rest my case. I rest my case. So there's another lesson there. If you don't like what the editor of a journal is telling you about your paper, call him up, talk to him. Don't just email him, get on the phone. And a lot of them will back off from things that they had been saying when you start to talk to them nicely and have a decent conversation. So anyway, that led in 1993 to the Nobel Prize, which I shared with Phil Sharp. He had made the same discovery, but completely independently. And that turned out to be good. Now, one of the things that happens when you have to go to Stockholm in order to pick up the Nobel Prize, you have to give a talk to the Nobel Committee. And so I had not worked on splicing for many, many years prior to this. And I'd become very interested in DNA methyltransferases. And when it came time to go and give the talk, I could have given a sort of boring historical talk about all the old stuff. But I thought, well, no, I'll talk about our latest discovery, because just 2 months before I had to go to give my talk, working with Xiaodong Cheng, an X-ray crystallographer at Cold Spring Harbor, we had discovered that when DNA methylases bind to DNA to methylate one of the bases, they flip the base 180 degrees right out of the helix. And this was the first time that this had been discovered. And so I thought, well, this is what I'm going to talk about. So that became my talk. I always was hoping that maybe someone would think that was another good reason for a Nobel Prize for myself and Xiaodong, but so far, no luck. Anyway, it was really a nice discovery to be made. And we actually wrote quite a bit about it. It turns out there are lots of enzymes that interact with DNA and flip the bases out into an enzyme pocket in order to do the enzymology. Now, I want to switch topics a little bit here and talk about New England Biolabs. So I was saying in my lab at Cold Spring Harbor, we were discovering all these restriction enzymes starting in 1973. And people were coming to meetings at Cold Spring Harbor with tubes of DNA in their pocket. They'd come down to my lab and they'd say, do you have an enzyme that might cut this? And so we got so used to this, we set up a little rack of enzymes and they could test it and do it and so on. And it was obvious. There were so many people who wanted these enzymes. And as soon as they found one that they thought was good for them, we would give them a sample of the enzyme, give them the strain, tell them how to make it and so on. And I mean, there were literally hundreds of requests coming in. In fact, we had a thermos that we were using to send samples out all over the country. And so I talked to Jim Watson, head of Cold Spring Harbor, and I said, look, what we should do is we should start a company here, make restriction enzymes, and then use the profits to support the research at Cold Spring Harbor. To which he told me I was crazy, that You can't possibly make money doing that sort of thing. Plus, it's really disgustingly dirty to be associated with industry. He didn't want anything to do with it. Now, of course, part of this was me, because he never really liked me when I started doing things he didn't want me to do. But at the same time, there was no doubt this would have been a good idea. So I talked to some friends at NIH, and someone told me they'd heard there was a guy in Boston who was going to make one of these restriction enzymes, actually the very first one that Ham Smith discovered. Why didn't I call him up? So I called him up, and he said, well, yeah, we're thinking about it, but we've not done anything yet. But why don't you come up and talk to us? At the time, we had 30 restriction enzymes that we discovered. Almost all of them were new specificities that were not known before. So I went up, I talked to him, and he was working in a basement. His name is Don Cohn, the guy on the left. He wasn't this old then. I went up in 1975, went down, and he was working in a basement in Beverly underneath a hairdressing salon. It was a little makeshift lab was there. He got a bit of equipment that from Harvard was selling off very cheaply all the stuff they didn't need anymore. And he had made a restriction enzyme. There was he, his wife, and one technician. They were making a living actually by lobster fishing and doing pregnancy tests. This was their big source of income. But he was a biochemist. And, we talked, and I told him about my ideas with Jim, and he said, and that was my idea. He said, when I started Biolabs, I wanted to use the profits to support research and set up a company and a lab that would be Harvard and NIH all in one place. And we will fund our own research. Don't need to go to NIH. We'll make the money and support it. And so that's how we got started. That's how NAB got started. I was their 4th employee. In the first year, they made $200,000 in sales, selling direct to customers. I gave them a list of names and addresses and so on. And now we do considerably more of that. No longer 4 people, we have 750 or so worldwide, and we have 370 working in Ipswich, which is where we now moved. At the time, I was on a commission. They gave me 10%. He said he was going to give me 10% of sales, not a profit, 10% of sales. Well, after 1 year, that got to be too much. And I said, you can't do this. So we agreed to drop it down to 1% of sales. And then that got too much. And then we settled on a standard fee over the year, with the money going down to Cold Spring Harbor to support my lab and the other labs on our floor at Cold Spring Harbor. So that worked out really well. In 1992, I moved up there to become research director. I was getting fed up at Cold Spring Harbor. I was thinking about starting a DNA sequencing company, and I had several people who were interested in this. But then Don heard, and he said, well, if you're going to go to a company, you've got to come and work for us. You can't go off and start something else. So I did. He made me an offer I couldn't refuse. I moved up there, and I've never regretted it. The only thing I regretted was not moving earlier. I mean, it's a wonderful company, wonderful place to be. So this was the very first catalog, which essentially I put together. It was pretty much all restriction endonucleases, 1 or 2 other things, but the restriction enzymes made all the money. Come on. Oh, it's very difficult to control this, at least for me. So now we started off in this basement, and then we built another lab in North Beverly, and then in 2005, we put up this brand new building, a huge building in Ipswich, moved on to this big estate. It used to be someone's rich American summer home, and put up the building, got an architectural firm to come in and put it up. The mansion there we used for administrative purposes. And we set up the whole lab thinking about the environment. Don was a great environmentalist. So for instance, we put in our own water purification system, solar purification. Now we have electric solar panels to provide the electricity. The water that comes out goes through a very extensive purification before it goes out into the environment. And we feed it into the Ipswich River, and it's cleaner than the water in the Ipswich River. So this was Don. He cared about nature. He wanted to do everything he possibly could to help nature. This is the company as it was a little while ago, 50 years old. Don Combe, the current CEO, is Sal Rossello. I'm the official CSO, but I'm really just a postdoc. You know, I got two people who do everything that a CSO normally does, so I can be a postdoc. I sit in front of my computer and do things every day. And it's a very cooperative environment. One of the things that I always like to say, we put in the very best healthcare scheme that we possibly could. We're very generous with overtime. With profit sharing, at the end of the year, we share out the profits among the employees. And the result is that the people who work there love working there. If you call and ask for a volunteer, you'll get 20. It's unbelievable. Everybody wants to help. And during COVID, we were making 3 of the enzymes that were used to make the COVID vaccine. We had to scale up our production 10,000-fold to meet demand. And so here you've got a normal production manager who was making on a small scale, needed help. And so we had no problems. All of a sudden, we've got 10, 20 people all wanted to help to make these enzymes. So for us, that was very good. You okay? Okay, so let me tell you a little bit about some of my other post-Nobel activities. I spent a lot of the Nobel money putting a croquet lawn in front of my house. I love croquet. And at the bottom is a picture of me sitting on the lawn dressed as Dr. December because I became one of the stud muffins of science. This was something I love to do. I enjoy this sort of thing very much. The Ig Nobel Awards, I go and participate in whenever I can. These are awards given not to Nobel Prize winners, but to people who do interesting science that you first look at it and it makes you laugh, and then you look at it a little more and you realize there's actually something deep in it. But the guy who runs it is really very good and very funny. I got a certain number of honorary degrees, one from the University of Bath, where I grew up. Never went to the university there. The school I went to, City of Bath Boys School, which I showed you, they put up a refurbished science wing that they named after me. Sheffield named one after me. I was knighted in Queen Elizabeth's 2008 birthday honours list, met by now King Charles at the time, Prince Charles. And I've got to tell you, that was a pretty scary experience because his hand was not as firm and still as you would like it to be. And that sword looked really sharp, but he managed not to take my head off, so it was okay. But one of the things I did, and one of the things I found after I won the Nobel Prize, was that people used to listen to me in ways that they didn't before. And I discovered this at press conferences and at other things. And I would make suggestions. Oh, maybe one should do this, or maybe one should do that. And I've always done this, but usually no one, may pretend to listen, but they never acted on it. And all of a sudden, people started acting on it. And so one of the things I did was to start to organize the Nobel laureates for good campaigns to do one of two things: to make science better or correct improper science, or for humanitarian causes. And one cause that came up were case of some Bulgarian nurses who had been put in jail in Libya. And they'd been accused of spreading HIV deliberately among children in the Benghazi Children's Hospital. Some 400 children became infected. And Gaddafi, president of Libya at the time, wanted to pretend it was really Mossad of Israel that had caused it, and then he backed off that. He couldn't make it up. But then he accused these Bulgarian nurses of doing it deliberately. They had a trial after having tortured these poor nurses. Several of them confessed to stop the torture, and the trial was just nonsense. They didn't have any good science there, and it was pretty clear that was going on. If you talk to people who'd worked in hospitals in Libya, Morocco, Algeria, and so on, they reused needles. And so what was happening is that someone had come into the hospital infected with HIV, and then they just spread it from one child to the next. And so I thought, well, this is something maybe the Nobel laureates can help. And so I called and talked to all the laureates. I got, I think, 125, all signed a letter that I sent to Gaddafi. I took it personally down to the Libyan ambassador to the United Nations. There was no embassy in Washington at the time. And I asked the ambassador, would he give it to Gaddafi, and explained the circumstances and so on. And basically it asked for a retrial and pointed out all of the defects with what had gone on so far. And he said, yes, he'd pass it on and it'd be okay. 2 weeks later, I get a call from Gaddafi's son who says, could you come to Libya and talk to us about this? So I hop on a plane, I go to Libya, spend a couple of days at the British Embassy there. They put me up, they were very nice. I'd already talked to people in the Foreign Office at London. I've got to say the Foreign Office here were not interested. They didn't want to know anything about this at all. So anyway, I stayed at the embassy and then got a call from Gaddafi's son and said, you know, I'm in this room, can you come over and meet me? We had about an hour's meeting, one-on-one, and at the end of it, he said, we're going to let them go. We know that they didn't do it. We know it's okay, it was an accident and so on. And so they got out of jail. And they were on death row at the time, so you can imagine this was pretty good. And I was so impressed with the fact that just speaking out against something like this with a lot of laureates could have an effect. And I've done now 50 campaigns with Nobel laureates. And the biggest one I'm doing at the moment is the one on GMOs. It's pro-GMO, to try to get people in the developing world to accept that GMOs are safe, that there's nothing wrong with them. And if anything, GMO crops are actually safer than traditionally bred crops, because we know we can make these GMO crops very safely at the moment. And so I have 183 laureates have all signed on to this campaign. We've been running it for 10 years now, and I think finally we're starting to see a little bit of success. So that's my current thing. But before I close, I just want to show and talk about the importance of luck. So billiards, I already told you about, okay? So I learned something important there. Kazuo Kurosawa, I mean, what luck to be put in the lab with a postdoc who is easily the best mentor I've ever had. He was fantastic. Went to Harvard instead of Wisconsin, quite by chance. What a piece of luck. Looking for eukaryotic promoters in adenovirus. We were looking for a promoter. The experiments we were trying to do failed. They didn't work. And that was because nature was trying to tell us something. And so I love it when students come to me and said, hey, you know, I did this experiment you suggested. It didn't work. I say, great, maybe nature's trying to tell us something else. So I'm a big advocate for failure. Failure is very good. Take an early plane is something I didn't tell you about, but you may remember 9/11 when there were a flight that went into the World Trade Towers. The very first flight, I was booked on it until 2 weeks before it took off because I was going to a meeting in California. They moved the meeting in California forward by 1 day. This was NASA who did this. And so I had to take an earlier plane, I had to change my ticket, and I went the day before on the plane that otherwise would have gone into the World Trade Center. So I was pretty lucky, I've got to say. The Unabomber. I don't know if you've heard about the Unabomber at all, but he liked to send letters and sometimes with bombs. His last act was to send out 5 letters. Phil Sharp got one, I got one, 3 other people got one of the others got a bomb. Again, that's luck. 1 in 5 chance, it could have been me. And finally, studying bacterial restriction modification systems. They really set the stage for my entire career. It's been very, very good. And I got involved in them, again, by luck, by chance, because I didn't want to do something that other people were doing. I wanted to try and find some other way of sequencing DNA. Excuse me. So that turned out pretty well too. So think about luck, take advantage of it when it comes your way. Think about failure. Failure is a good thing. This is when you learn. You know, there's a fellow called Bill Gates who started a company many, many years ago. His first company failed, but his second company did okay. So there are many things that can happen. And it's worth looking back and asking yourself, have I always taken advantage of the luck that came my way? So I wish you all the luck in the world. And I just want to show one last slide. This is about women in science. I think we all know that over the years, women have not been treated very well in science. And I think in many cases in the earlier days, it was because it was almost deliberate. But also there have been lots of times when we men do not treat women properly, and I'm as guilty as anybody, because we think if we treat them like men, then we're treating them well. But women are not men. Women have periods, they have children. They need accommodations that we as men don't need. And I think these are books that I would recommend. The Exception is a very nice story about Nancy Hopkins at MIT and her fight for women at MIT. Picture a Scientist is a short documentary that features Nancy Hopkins very carefully. Breaking Through by Kadi Kariko is very good. She got the Nobel Prize a couple of years ago for messenger RNA. If you read her story, you'd be surprised that she was ever able to do anything that would lead to a Nobel Prize. She was incredible. Bottom one is Rita Colwell, who was head of NSF for a long time. That book is very good. And the one in the middle, Invisible Women, covers not just science, but it covers the whole spectrum of women in society being treated badly. And I would recommend everybody to read these, but especially the men, because we often do things that we think we're treating women properly, and we're not as fair as we might be. So, thank you. Pardon?